Hello and welcome to the final part of EGM310, Terrestrial Remote Sensing. In this part of the module, we'll cover the fundamentals of terrestrial remote sensing and how we can apply remote sensing techniques to complement or enrich our research. To make things a bit easier to digest this semester, I've broken the lecture this week into 5 smaller pieces, each of which has its own video and slides. The theme for this week is Fundamentals of Remote Sensing. In this first video, we'll cover what terrestrial remote sensing is and why we're learning about it. Just as a note, I will most likely drop the terrestrial portion of the name and just use remote sensing as a shorthand. In the next videos, we'll cover the basics of electromagnetic radiation, how it interacts with both the Earth's atmosphere and objects on the Earth's surface, and finally, we'll cover the spectral properties of objects. For each of these mini lectures, I've also included some links to additional resources, including YouTube videos that cover some of the different topics, as well as the chapters in a few textbooks that cover the same material. If you download the lecture slides from Blackboard, you should be able to get the links to the different videos or websites, but I've also included these links in the description below each of the videos. With that out of the way, let's get started with the first topic. What is terrestrial remote sensing, and why are we studying it? To begin with, think about some of the ways that we acquire data or information about the topics that we study. We might work in a laboratory, conducting experiments or analyzing data. We might go out and conduct surveys, interviewing people to learn about different aspects of our topic, or we might go out and conduct field work, taking measurements and acquiring data in the field. Each of these different methods gives us detailed, accurate, fine-grained information. They allow us to study small-scale processes, but can be very difficult to scale from the small scale to the regional or global scales. For example, measurements we make in one river catchment or one lake don't necessarily tell us anything about another river catchment or another lake just a few kilometers away. In addition, fieldwork can be dangerous, difficult, or expensive. If we want to make the same measurements in another area, we might have to buy duplicate equipment, we might have to make multiple trips to service and move equipment, and so on. Sometimes, such as now, travel isn't feasible or even possible. So, if we can't travel to the thing that we're studying, how can we study it? On this slide, I've put a few different textbook definitions of remote sensing, and I've highlighted some of the important words. So the first one here is from Jensen, relatively short, and the next one is from the International Society for Photogrammetry and Remote Sensing, and it's quite a bit longer and a bit more detailed. You can see from the highlighted words between the two that the basic meaning of remote sensing is, as the name might suggest, studying something without having to touch it or travel to it directly. So that a bit answers our question, how can we study things without going to them? Are we new to remote sensing? No, not at all. In a way, this is something that we've all been doing for years. Aside from touch or taste, all of our other senses involve collecting information about the world without touching it directly. Remote sensing gives us a unique perspective on the Earth and environment. Rather than seeing things at ground level, remote sensing gives us an overhead, bird's-eye perspective. This can enable us to see patterns or relationships that aren't immediately clear at ground level. It also allows us to observe or study areas that are too dangerous or difficult or costly to travel to. For example, we can use remote sensing to study active, erupting volcanoes, study hurricanes and other storms and their impacts, or map wildfires on a global scale. With multiple images, we can analyze changes over time, mapping large areas quickly and cheaply. Finally, remote sensing allows us to map the Earth system on a global scale. As a first example, let's say we want to map the extent of Vatnajökull, the second largest glacier in Europe by area. Now, we could take a GPS, throw it in our backpacks, and walk around the perimeter of the glacier. If we're feeling a bit lazy, we could try driving it instead. Of course, this is a huge distance that we'd have to walk, and it's not easy ground to cover. There are large rivers to cross, it's steep and rocky in areas, and it would probably take several days to cover the entire glacier. And then what happens when we want to do the whole thing again later? This is to say nothing of mapping the other glaciers on Iceland, some of which you can see in this image here. From this direct method, we also can't make any measurements back in time. The good news is, we can map the glacier extent of Vatnajökull and other glaciers in just a few hours or even faster using satellite images. With some of the data sets that we'll talk about in this part of the module, we can even map the glacier extents back to the early 1970s using satellite images. Another example of the power of remote sensing is from archaeology. As you might imagine, mapping the full extent of ancient monuments or cities can be difficult, painstaking work if it's done in the field. This is especially true in tropical regions, such as the example shown here. Over hundreds or thousands of years, forests can cover over human activity, erasing any traces. In this satellite image, we can clearly see some modern developments. We have roads up here at the top of the image, a canal running down the eastern portion of the image, some different agricultural fields, but we can't really see much of anything else. Using a technique called LiDAR, more on that later, scientists have recently discovered the ruins of a number of large monuments and cities in the rainforests of Central America. This example here, a site called Aguada Phoenix in southern Mexico, was built between 1000 and 800 BC and abandoned around 750 BC. The main plateau here is about 1400 meters long and about 10 to 15 meters high. Think about how much work it would be to excavate and map this site without the benefit of remote sensing. In week 12, we'll look at a number of different studies that apply remote sensing techniques to a wide array of topics. So remote sensing is any way of capturing information at a distance. It lets us quickly and easily monitor changes at large scales, including across the globe. The sensors that we use for remote sensing can be almost anything. They can be cameras, laser scanners, radar, other instrumentation, anything that lets us acquire data from a distance. In this module, we'll mostly be focusing on imaging from optical or visible and infrared remote sensors, although we'll touch on some of the other examples. Remote sensing depends on a number of things, all of which make up a part of the process or system of remote sensing. These include a radiation source, often the sun, but it can also be the sensor itself. This includes the Earth's atmosphere, the different features or surfaces on the ground, as well as their properties, and of course the different interactions between all of these things. The system also includes the transfer and storage of the data, as well as the actual analysis of the data. In 2 of the textbooks recommended for this course, Lillesand, Kiefer and Chipman, and Campbell and Wynne, more information about remote sensing and the remote sensing process is found in Chapter 1. There's also a link here to the remote sensing tutorials provided by Natural Resources Canada, which have some good introductory information and quiz questions you can use as you study. Finally, there are 2 different YouTube videos from Climabyte and Sires which try to answer the question, what is remote sensing? That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!